Welcome, curious minds, to the deep dive. And welcome back to the Neural Intel podcast. Our mission, as always, is to take these really complex topics, cut through the noise, and just distill the most important, insightful, maybe even surprising nuggets of knowledge. We're really here to give you that shortcut to being truly well-informed, custom-tailored for you, our listener. Today, we're plunging into something pretty incredible, honestly. It feels almost magical sometimes, the ability of large language models, LLMs, to learn new things on the fly, like right there in the prompt you give them, even stuff they haven't been explicitly trained on. This whole thing is known as in-context learning, or ICL. It's genuinely one of the most striking features of modern LLMs, but also, well, one of the most theoretically mysterious. It feels like the model is genuinely reorganizing its intelligence right there in real time. So today, we're taking a deep dive into the technical heart of in-context learning. We're going to unpack a fascinating new research paper. It sheds some real light on how these LLMs seem to learn without that explicit traditional training we usually think about. And just to be clear, we'll be focusing purely on the mechanics here, the implications for the technology itself, and what this might mean for the future of AI from a technical standpoint. This is exactly the kind of cutting-edge AI and ML research we love digging into here on the Neural Intel podcast. We're keeping our focus squarely on the tech, avoiding the broader societal debates to really hone in on the engineering and scientific breakthroughs. Okay, so let's try and unpack this core mystery a bit, because in traditional machine learning, right, learning means something very specific. It means updating a model's internal weights, billions of them sometimes, through this complex, often really lengthy optimization process. It chews up vast amounts of data, tons of compute power. We're talking backpropagation, gradient descent, fundamentally changing those parameters.
Right. It's a whole process. You train it, you update it, you bake that knowledge in.
Exactly. But with in-context learning, the LLM adapts at inference time. That's when you're just using the model, asking it questions. It learns from examples you give it directly in the prompt. And here's the kicker. There are no immediate explicit weight updates happening. It's not retraining.
It's like it just reorganizes itself on the fly, dynamically reconfigures its internal state based purely on your input.
Without going back to the drawing board, how does that even work? What's the hidden mechanism?
Yeah, that really has been the million-dollar question for ages in understanding these huge models.
And just a reminder for everyone listening, for more deep dives into this kind of cutting-edge AI and ML research, do remember to visit our webpage. The link's right there in the bio.
Okay, so the paper we're diving into today, it's called Learning Without Training, the Implicit Dynamics of In-Context Learning. It's by Domiran and colleagues from Google Research. And they propose this really powerful and, I have to say, incredibly elegant theory to try and answer that exact question. Their core hypothesis is this. The simple stacking of a self-attention layer with a multi-layer perceptron and MLP, just that structure within a standard transformer block, allows it to implicitly modify the MLP layer's weights, and it modifies them based on the context you provide in the prompt.
Implicitly modify the weight, so not an explicit update command, but the context itself causes a change.
Exactly. And it's not just a vague idea. They provide a concrete mathematical framework for how this implicit modification actually happens. It might just be the fundamental underlying reason LLMs learn in context. It offers a tangible mechanism for what before just felt like this emergent, almost magical, unexplained thing.
Okay, so let's really nail down what in-context learning is first. We touched on it, but to fully grasp why this paper is such a big deal, let's unpack ICL itself a bit more. What exactly makes it so different, so breakthrough compared to traditional learning, and why has it been such a puzzle?
Right. So in context learning, ICL is fundamentally the ability of an LLM after its main pre-training is completely finished. So think of it like its weights are frozen at this point.
Okay, training's done, model is set.
Exactly. And then it can learn new patterns or even entirely new tasks just from examples given directly within the prompt itself. And it's absolutely crucial to get this. These specific patterns or tasks might have been completely absent, or at least not explicitly represented, during its huge foundational pre-training phase.
So it's learning genuinely new stuff, not just recalling variations of things it already saw.
That's the claim, yes. Think of it like this. You've built this incredibly powerful general-purpose computer. In traditional machine learning, if you wanted that computer to learn a new specialized skill, you'd have to, metaphorically speaking, physically rewire parts of its circuitry. You'd have to retrain it. With ICL, it's as if you could just tell the computer a few examples of this new skill right there in text, and it instantly reconfigures its internal operations to perform that skill, without ever touching its underlying hardware, its frozen weights.
Wow. Yeah, the distinction from traditional machine learning is really stark when you put it like that, because traditionally, like you said, if you wanted a model to learn, I don't know, how to translate some obscure dialect, you'd kick off a whole new training loop. You'd need massive data sets, lots of compute time, maybe fine-tuning.
Precisely. Historically, learning in machine learning meant that dynamic iterative process where the model's weights, those billions of numbers, were updated through a deliberate optimization procedure, usually using algorithms like stochastic gradient descent, consuming examples over many, many passes, computationally intensive backpropagation to adjust every single parameter. It's a fundamental, persistent change to the model's core parameters. That knowledge is baked in for future use.
Okay.
But the profound mystery of ICL is that there's no overt, explicit weight update happening at inference time. The model isn't being retrained in that sense, yet it appears to reconfigure itself dynamically based purely on user prompts without any of that heavy-duty computation we associate with explicit training. It's really a different beast altogether.
So for years, researchers have been trying to crack this ICL code, right? Proposing different theories. What were some of those earlier ideas and where did they kind of fall short?
Yeah, there's been a lot of head-scratching. For quite some time, the main thought was, okay, there must be some kind of implicit form of weight updates happening. Even if we can't directly see them or measure them easily, it was more of a hypothesis, a strong hunch. Some early work using very simplified, what we call toy models of transformer blocks. Think like a really stripped down basic version of a real LLM.
With the lab experiment version.
Exactly. Those studies showed that these simplified structures could implicitly perform something that looked a lot like gradient descent. There were studies, for example, suggesting that the act of the model processing a prompt could be mathematically identified with steps of gradient descent, maybe on some kind of least squares loss function related to the prompt examples.
Ah, so the prompt itself acts like mini training data for these implicit steps.
That was the idea. And it was exciting because it potentially linked this mysterious emergent behavior, ICL, back to a core foundational concept in machine learning gradient descent.
But I remember there was a big debate around this too, wasn't there? Like, is this true learning or is it just the model being clever with what it already knows? The whole retrieval versus true learning thing.
Oh yeah, that's a critical point and honestly still debated in some corners. Some researchers argued pretty strongly that ICL wasn't true learning, not in the sense of acquiring genuinely new knowledge or skills. Instead, they proposed it was more like the model was just retrieving pre-trained capabilities that were already sort of latent, buried within its massive knowledge base, or maybe performing a type of Bayesian conditioning based on the prompt.
How did they test that idea?
Well, some early studies did something quite clever. They took the prompts, the examples given to the model, and they replaced the correct labels with random ones, basically feeding it nonsense instructions.
Okay.
And they found that in some cases, the model's performance didn't actually drop that much.
Whoa, so giving it wrong examples didn't break it.
Not entirely, in those specific studies, which seemed to support the retrieval argument, right? It suggested the model was relying more on its existing pre-trained understanding of language structure and patterns rather than truly learning the specific and now corrupted relationship shown in the examples, like sophisticated pattern matching, not genuine acquisition of the wrong rule.
So if you showed it examples like cat means dog, and it still mostly worked okay, it suggests it wasn't actually learning cat equals dog, but just using its background knowledge about animals or concepts.
That was the interpretation, yeah. However, more recent, and frankly more sophisticated research has really challenged that view. Newer studies have shown that larger models in particular do actually start to learn from those randomly switched labels, even if the labels seem nonsensical to us.
Ah, so the bigger the model, the more it seems to actually adapt, even to weird inputs.
It seems that way. Which indicates genuine adaptation, something beyond just retrieving what it already knew. And there's also evidence suggesting that the emergence of true ICL depends quite heavily on the sheer diversity of the data the model was pre-trained on. So the picture's way more complex than simple retrieval. It looks like a dynamic interplay between the model's vast pre-existing knowledge and this ability to adapt on the fly based on the immediate context.
Okay, that makes sense. And what about those earlier toy models that showed the implicit gradient descent? Were they just too simple to capture the full picture in big, real-world LLMs?
Yes, that was definitely another significant limitation. Many of those prior theories, while insightful, relied on pretty narrow assumptions. They often focused only on the linear layers within the model, ignoring the nonlinear parts, which are crucial. Or they assumed prompts were constructed only of very specific, artificial pairs of examples, like for a simple regression task.
Which isn't how we actually use these models with natural language.
Exactly. These assumptions, as various researchers pointed out, just aren't realistic for the actual complex LLMs that process messy, diverse, nonlinear natural language. They highlighted cases where ICL's observed behavior didn't quite match true gradient descent if you tried to construct a more realistic fine-tuning loss from the prompt examples. So while those toy models gave us some really valuable early glimpses, they couldn't fully explain the breadth and the subtlety of ICL in the huge, general-purpose language models we use today. This is why a more generalized theory, like the one in this paper, was really needed.
Right. Which brings us back to the Darren paper. It sounds like they took a totally different path, trying to move beyond those specific narrow assumptions.
They absolutely did. Instead of abstracting down even further into simpler toy models, this work kind of goes up the abstraction road, as they put it. They introduced this concept of a contextual block. Think of it as a powerful generalization of a standard transformer block. The key idea is to abstract the essential contextual property of a layer like self-attention. They focus on how a layer's output changes when context is provided versus when it isn't, rather than getting bogged down in the specific mathematical details of self-attention itself.
So it's a higher level view, focusing on the function how context influences output, rather than the exact mechanism.
Precisely. And by doing this, by generalizing to this contextual block, they managed to remove those limiting assumptions about needing linear layers or specific types of prompts that hampered earlier theories. This abstract approach allows their theory to apply to completely generic prompts, the kind you and I actually use.
That sounds like a huge step forward, bringing the theory much closer to reality.
It really is. It validates that the underlying principles might hold even for the messy, nonlinear world of real language and real prompts. But there's a key conceptual shift, a trade-off maybe. The implicit dynamics, the learning, is now understood to take place primarily on the MLP layer that follows the attention layer, not solely within the self-attention layer itself, which was the focus of some previous work.
Ah, okay. So the attention layer processes the context, and then its output implicitly modifies the next layer, the MLP.
That's the core idea they developed. This refocusing of where the implicit updates actually happen is central to their generalized theory.
Got it. That's a really important distinction. So let's dive into this contextual block concept properly and get to their core discovery. How do they define these key components, the contextual layer, the block itself, and how do they work together for this implicit learning?
Okay, so at the heart of it, the paper defines what they call a contextual layer, A. Think of this as any network layer that's designed to process information in two ways. It can take a single input vector, let's call it X by itself, and produce an output, AX. Or, crucially, it can take that same input vector X combined with some context, let's call that C, and that produces a potentially different output, ACX.
Okay, so the output changes depending on whether context C is present.
Exactly. And the difference between those two outputs, they denoted AECXAX, this AAC, represents the direct effect, the modification, that the context C has on the layer's output, specifically for that query token X. It quantifies the context influence.
Can you give us a more concrete example? Like, how does this map onto a real transformer?
Sure. In a typical transformer, the self-attention layer is a perfect example of a contextual layer A. In this case, C would be the sequence of context tokens. Maybe it's an instruction like translate the following into German, or it could be the entire preceding conversation history.
Right, the stuff that came before the token we're predicting now.
Exactly. And X is the specific query token for which the LLM is about to make its next prediction. So that LAC calculation then measures exactly how the presence of that instruction prompt or conversation CC changes the attention layer's output for the query token X compared to how X would have been processed in isolation without that context. It's like the numerical fingerprint of the context influence at that point.
Okay, so you have this contextual layer, the attention layer, which is influenced by the context C, and then this output is fed into a standard neural network part to form what they call the contextual block.
That's right. They define a contextual block, TW equals MWAA, as the composition, the chaining together of this contextual layer A with a standard neural network block, MW. Now, this MW network has a specific structure in their definition. MWZ is defined as beta UZ plus B. Here, WB are specifically the weights and biases of the first fully connected dense layer within that MW block.
Okay, just the first layer's weights.
Yes. And Phi represents everything else in that block, subsequent layers, the nonlinear activation functions, maybe layer normalization, etc. This structure cleverly generalizes the full transformer block. It abstracts it in a way that lets them make their theoretical breakthroughs while still mapping closely to the real architecture. And that pho part is crucial, of course, because that's what gives neural networks their power to learn complex nonlinear relationships.
All right, here we go. This is where it gets really juicy, right? With these components define the contextual AA and the network block MW, what's the massive discovery? Theorem 2.2. This is the core mechanism they propose for ICL.
This is absolutely the core theoretical insight. The paper proves mathematically that this contextual block structure implicitly transforms a portion of the context, let's call that portion Y, into an update of the neural network's weights. Specifically, it updates the weights W of that first fully connected dense layer within the MW network.
Wow. Okay, hold on. The context isn't just an input signal anymore. It's actively, implicitly changing the weights of the network.
That's precisely the claim. The context is literally rewiring a small part of the network's knowledge base, just for that specific interaction.
So the prompt is, in a way, momentarily reprogramming the model. That's a big shift in thinking. And they have a formula for this weight update, JWY.
They do. We don't need to get lost in the exact equation, but conceptually, the formula AWY calculates precisely how that piece of context Y translates directly into a very specific change within the MLP's weight matrix W. It shows mathematically how the context reshapes the network's processing for the subsequent query. But the most crucial part of this EWY, the property they prove, is that it's always a rank 1 matrix.
Rank 1 matrix. Okay, refresh my linear algebra. What does that mean practically? Why is rank 1 important here?
It's super important. A rank 1 matrix represents an incredibly simple, low-dimensional modification to the existing weight matrix W. Think of it like this. Instead of having to tweak thousands or millions of individual parameters in W independently, a rank 1 update is like adjusting a single coordinated pattern across all those weights. It's a very structured, focused change.
Ah, okay. So it's not a messy, arbitrary update everywhere, but a very targeted, efficient adjustment.
Exactly. Highly efficient, highly targeted. The implications are huge. This suggests that contextual layers like self-attention are effectively performing a kind of implicit fine-tuning of the MLP weights that follow them. The update EWY is computed directly from the context Y. It's as if the context itself is reprogramming a specific slice of the network's knowledge for that particular interaction and doing it in this highly efficient, low-rank way.
Yeah.
It really changes how we think about adaptation in LLMs.
That's a massive insight. It makes the reprogramming sound less like a heavy lift and more like a nimble surgical adjustment. And you mentioned earlier, this theorem isn't just limited to self-attention, right? It applies more broadly. That makes it even more fundamental.
It does. And this raises that really important question you touched on. What does it mean for ICL to be a deep property of neural nets, allowing input modifications to become weight modifications? How does this simplify things compared to attention-specific theories? And what are the technical benefits of this low-rank update? Well, first, Theorem 2.2 is remarkably general. It applies to any layer that fits their definition of a contextual layer. So yes, that includes things like recurrent neural networks, RNNs, or even newer architectures like Griffin models with recurrent layers and local attention. This strongly suggests that ICL isn't solely dependent on the unique, intricate machinery of self-attention, which, has often been seen as the special sauce.
Right. People often point to attention as the reason for ICL.
But this paper suggests it's maybe more fundamental. It points towards a deeper property of neural networks in general. Their inherent ability to translate modifications in their input space directly into changes within their internal weight structure. This connection between input changes and weight changes has actually popped up in other theoretical work trying to explain why deep neural networks generalize so well.
So ICL might be one manifestation of a broader principle about how neural nets learn and adapt. That definitely simplifies the picture, moving beyond just transformers.
Exactly. It frames ICL less as an architectural quirk and more as a core computational capability. And the technical benefit of the update being low rank, rank 1 specifically, is its computational efficiency and structure. It implies a targeted, computationally cheaper modification compared to, say, a full rank update that would change the weights in a much more complex, arbitrary way. It's an elegant solution.
Okay, so it's a fundamental property, applicable beyond just attention, and involves these efficient low-rank updates. Makes sense? And they also showed this applies to the entire context, corollary 2.3.1.
Yes, exactly. The theorem also provides a formula for transferring the effect of the entire context C into the MLP's weights. It shows that TWCX, that's the output, when the full context C is explicitly fed in along with the query X, is mathematically identical to TW plus EWCX. Here, EWC is also a rank 1 matrix, but this time it's derived from the full context C.
So the entire context, no matter how long or complex, can essentially be compiled down into a single, simple rank 1 update to the MLP weights for that specific query.
That's what the math shows. It demonstrates the incredible elegance and potential efficiency of this implicit mechanism. The model doesn't necessarily need to keep juggling the entire raw context. It can effectively absorb its influence into this compact weight modification.
That's quite something. It suggests a different way the model might be remembering or using context. Now, moving on from this core mechanism, how does this work iteratively? In the real world, prompts are sequences of tokens, right? Does this lead to a step-by-step learning process?
Yes, it absolutely does. And this is where the dynamics become really interesting, painting a picture of learning unfolding over time as the prompt is read. When the context C is a sequence of tokens, let's say C1, C2, BACN, they show that applying this weight transfer formula iteratively reveals what they term an implicit learning dynamics. You start with the initial MLP weights, W0. When the model processes the first token C1, the weights implicitly become W1 equals W0 plus EW0, C1. Then, when it processes C1 and C2, the weights implicitly adjust further to W2 equals 00 plus EWSC1, C2.
So the update incorporates the cumulative context up to that point.
Exactly. This continues step by step until you reach WN, which incorporates the influence of the entire context sequence from C1 through Cn. And the paper rigorously demonstrates that the final output calculated using these implicitly updated weights, Wn, without the explicit context C, is mathematically identical to the output you'd get from the original contextual block, processing the full context C from the start.
So it's like the model is genuinely learning or refining its internal state and steps, dynamically adjusting its understanding of the task just by consuming the prompt token by token. That's wild. And the paper even connects this iterative process to gradient descent, which is just profound given how central gradient descent is to all of traditional machine learning.
It's a stunning connection. Proposition 3.1 in the paper demonstrates that this implicit learning process can be formally realized as a type of stochastic gradient update. When you look at the mathematical form of the weight update at each step, y1 hwy1, it looks exactly like a standard gradient descent step used in explicit training.
Wow. Okay, so what corresponds to the learning rate and the loss function in this implicit version?
Good question. The learning rate in this analogy is derived from the contextual layer's output specifically. It's related to 1 divided by the squared norm of AX, which you can think of as related to the strength of the contextual layer's output for the query token alone. And the loss function at each step, the deleo, is implicitly defined by something called AI, which fundamentally measures the effect or the surprise of adding the next context token psi.
So the model is implicitly trying to minimize the surprise or error introduced by each new piece of context.
That's a great way to think about it. And a really key observation they make is that these implicit gradients actually get smaller and eventually vanish as the dynamics progresses and converges towards incorporating the whole context.
Just like real gradient descent, the updates get smaller as you approach the minimum.
Precisely. It's exactly what you'd expect from a well-behaved optimization process. It indicates that the model has effectively learned or integrated the information from the context fully, reaching a stable state for that prompt.
That's incredibly powerful, showing this deep mathematical analogy between an on-the-fly, seemingly emergent behavior and the core mechanism of explicit training. It really grounds ICL. But the paper also mentions an alternative dynamic, right? Something explored in their appendix that isn't directly framed as gradient updates. So what's the significance of having both? Why explore a gradient descent-like view and this other factorization dynamics? How do these different theoretical lenses help us understand what's going on inside? And thinking technically again, what might the paper not discuss regarding potential computational differences between these implicit dynamics? Like, even if they lead to the same result, is one potentially more costly for the model to compute internally during that forward pass?
That's a really insightful technical question. Having both perspectives is actually quite valuable for building a comprehensive theoretical understanding. The gradient descent analogy is incredibly intuitive, right? It connects ICL directly to this foundational optimization process we understand so well from traditional ML. It suggests LLMs are implicitly optimizing some kind of loss function defined by the prompt context. That gives us a familiar framework.
It makes it feel less like magic and more like optimization.
Exactly. It implies the model is trying to minimize some internal measure of error or inconsistency with respect to the context examples it's seeing. Now, the alternative dynamics, the one based on factorization, which is an explicitly gradient descent, offers a different mathematical viewpoint. It leads to this formula. What do ON equals W0, 1 plus H1A1, 1 plus H2A2, 1 plus H and NA. This perspective highlights the multiplicative way that information from sequential tokens can build up and progressively transform the MLP weights. It shows how the influence of each piece of context sort of compounds over time.
So one view is like taking steps down a hill, gradient descent. The other is like applying a series of transformations, factorization.
That's a decent analogy. Together, they demonstrate the richness of these implicit mechanisms. One emphasizes an optimization path, the other a compounding effect. Both lead to the same end state, but give different insights into the process. Now, regarding your really sharp point about computational implications, the paper focuses primarily on proving the theoretical equivalence of the final outputs. It doesn't explicitly quantify whether the actual internal computations that achieve TWCX standard processing are inherently more or less resource-intensive than somehow explicitly computing TW plus AWX during inference.
Right. We know the implicit way is way faster than external fine-tuning, but what about the cost inside the forward pass itself?
Exactly. While the implicit process avoids the massive cost of backpropagation across the whole network, calculating the E-shay to C, or forming the Curie-T matrix implicitly within the forward pass of a transformer block, still involves computations. Are these computations, like matrix multiplications needed to form he to W, a significant overhead compared to a standard forward pass without this implicit update perspective? The paper doesn't really delve into benchmarking that internal cost. It's certainly vastly more efficient than explicit fine-tuning, but whether it's a negligible cost or a non-trivial fraction of the total inference compute, especially for very large models in extremely long contexts, is a critical technical question for future investigation. It impacts real-world deployment and scaling.
Okay, that makes perfect sense. It sounds like they've built this really solid theoretical foundation linking ICL to core ML concepts, showing these dynamics. But theory is one thing. How do they actually go about verifying it? What experiments did they run to see if this math holds up in practice?
Right, the crucial step, empirical validation. To test their theory, the researchers set up experiments using a very well-defined controlled problem. Getting a transformer to learn a class of simple linear functions just from examples given in the context.
Linear functions, like y equal mx plus b, kind of simple. Why that?
Exactly, that kind of simplicity. They chose linear functions very deliberately because previous research had already clearly established that standard transformers are capable of learning these simple linear models in context. This gave them a perfect controlled laboratory setting. They knew the task was solvable via ICL, so they could focus purely on testing whether their proposed mechanism, the implicit weight update, accurately explained how the model solved it, without the noise and complexity of, say, natural language generation.
Got it. So instead of a broad, messy task like summarizing text, they picked a precise, measurable task where they could really isolate and track the effect predicted by their theory. Smart.
Very smart. The prompts they used were structured. They contained input-output pairs, like hxy, where hx was a specific linear function, hx eats wx, followed by a final query input, xquery. The model's task was straightforward. Predict the correct output, hxquery, using only the examples provided in that same prompt. No explicit training on that specific linear function h beforehand. And for their main experiments, they even used a slightly simplified transformer block, specifically one without the standard skip connection around the MLP layer.
Ah, does that matter?
Well, skipped connections are important in deep learning, but removing it simplified the analysis. Crucially, though, they went back and confirmed in their Appendix A that the core theory still holds even with the skip connection present. So the simplification didn't invalidate the main finding.
Okay, good. So they have this controlled setup. What was the absolute key test, the moment of truth for Theorem 2.2? Did the model's normal prediction match the prediction made using their implicitly updated weights?
That was precisely the crux of their empirical validation. The critical comparison was, 1. The model's prediction made the standard way, processing the full in-context prompt, TWCX, in their math. 2. The prediction made by taking the same model, but calculating the implicit weight update, WC, using their formula, applying that update to the MLP weights, W, and then feeding only the query X into this modified model, TW plus EWCX. If their theory was correct, the outputs from these two methods should be essentially identical.
Were they? Did the experiment bear out the theory?
The results were apparently striking. As shown visually in Figure 1 of their paper, they found the outcomes were in remarkable agreement. They tracked the validation loss, basically how wrong the predictions were for both methods throughout the training process, where the model learns to perform ICL better. The loss curves for both the standard method and the implicit update method tracked each other incredibly closely.
Wow, that's strong evidence.
It really is. It's a powerful empirical confirmation of their theoretical formula. It strongly suggests that the implicit weight update mechanism they derived isn't just a mathematical curiosity. It accurately captures the functional effect of the in-context prompt. The model behaves as if it's dynamically rewiring itself in exactly the way the theory predicts.
That's very compelling. It bridges the gap from abstract math to measurable behavior. They also looked at the convergence of that weight update AAW, right, as more context tokens were added. What were they hoping to see there, based on that gradient descent analogy?
Yes, they dug into the dynamics. Based on the gradient descent analogy we discussed, the expectation was clear. The gradient updates, which here corresponds to the change in AW caused by adding just one more context token, should get smaller and smaller, eventually vanishing as the model processes more and more of the prompt. Just like in optimization, as you get closer to the target, fully incorporating the context, the steps you need to take should shrink.
Did that happen? It did. Figure 2, in their paper, visually confirms this beautifully. They plotted the L2 norm, which is just a standard way to measure the overall size or magnitude of the difference between successive implicit weight updates. And just as expected, the magnitude of this difference consistently decreased and converged towards 0 as more context tokens were processed. It mirrors exactly what you'd see in a well-behaved converging gradient descent process, adding yet more weight to that analogy.
Okay, consistent results there too. And then the comparison that feels most relevant for practical implications. How did this implicit learning happening on the fly within the prompt stack up against good old-fashioned explicit fine-tuning? Yes, this was a really fascinating part of their study, comparing the implicit process directly to traditional optimization. What they did was, first, pre-train a transformer model generally. Then, they created a completely new linear function task that the model had definitely never seen during pre-training. Then they ran 2 parallel adaptation experiments on this new task. One, explicit fine-tuning. They took the pre-trained model and explicitly fine-tuned it on batches of examples from this new linear task, step by step. Crucially, they only updated the weights of the MLP layer during this fine-tuning, carefully mimicking where their theory says the implicit updates occur. This gave them a gradient descent, GD test loss curve. 2, implicit ICL. They used their implicit weight transfer formula to calculate the effective MLP weights based on the same context lengths used in the fine-tuning steps and measured the model's performance using these implicitly updated weights. This gave them a GW test loss curve.
All right, this is where it gets really interesting for the future, isn't it? What did that comparison show? And let's really think about the purely technical implications here. If ICL truly mimics explicit fine-tuning this closely, does that open the door to achieving customized, fine-tuned performance purely through clever prompt engineering someday? Could it change how we even design model architectures? And again, that crucial question, what might the paper not be telling us about the resource differences? Explicit fine-tuning is notoriously heavy. Is this implicit version truly lightweight in comparison, even if functionally similar?
Okay, so the results shown in Figure 3 are quite revealing. While the exact numerical values of the loss weren't identical between the implicit explicit GD methods, the way the loss decreased as more context examples were provided was strikingly similar. The learning curves had very comparable shapes and trends. This is a seriously significant finding. It suggests that, at least within this controlled linear function setting, ICL isn't just doing something vaguely useful. It's functionally achieving an outcome that is profoundly similar to what you get from traditional explicit optimization. It's reaching comparable levels of task adaptation through this entirely different in-context mechanism. Now, for the practical technical implications, if ICL can indeed functionally mirror explicit fine-tuning, even partially, it's huge. It really does fuel the idea that we might achieve highly customized model behavior without needing separate, costly fine-tuning runs for every specific task or dataset.
Like fine-tuning via prompting.
Exactly. Imagine crafting sophisticated prompts rich with examples that effectively fine-tune a base model for your specific need right there at inference time. This could make LLMs incredibly agile, adaptable, maybe even enabling things like hyper-personalization for individual users without needing massive back-end infrastructure for continuous retraining. It could also strongly influence future LLM architecture design. If we know context implicitly updates MLP weights in this low-rank way, maybe we can design transformer blocks that are even better at facilitating this. optimize the interplay between attention and MLP for more effective implicit learning. However, coming back to your critical point about resources, the paper demonstrates functional similarity in learning outcome, but doesn't explicitly benchmark the computational cost of the implicit process versus the explicit one.
Right. Fine-tuning these backprop gradients, big updates.
Yeah.
Very expensive.
Precisely. The implicit process happens within the forward pass. It avoids all that backprop. But calculating Ly and forming Ly implicitly still requires computation during inference. Is that computation significant? Does it add latency? How does it scale with model size, sequence length, prompt complexity? These are vital technical questions the paper doesn't quantify. While implicit ICL is undoubtedly orders of magnitude more efficient than a full external fine-tuning run, whether its internal computational overhead within the forward pass is truly negligible or becomes a bottleneck for massive models and very long contexts is crucial for real-world deployment and scalability. That needs further investigation.
That distinction between functional similarity and computational cost is absolutely key for engineers building these systems. Okay, so let's try and wrap this up. Stepping back, what are the main advancements and the broader technical implications we should take away from this paper? How does it fundamentally shift our understanding of LLMs?
I think the key advancement is that it significantly pushes forward our mechanistic understanding of ICL. By developing this theory around the contextual block and implicit MLP updates, they've managed to move beyond many of the limiting assumptions of previous work. Crucially, their theory holds for different types of contextual layers, not just self-attention. This really broadens its applicability and suggests ICL isn't solely a trick of the transformer architecture. It fundamentally shifts the perspective. ICL might not be just about the complex wiring of self-attention. Instead, it seems to be a manifestation of a deeper, perhaps more universal property of neural networks, their ability to translate changes in their input directly into structured changes in their internal weights.
Like a fundamental aspect of how they generalize and adapt.
Exactly. It connects ICL to broader principles of neural network dynamics and generalization. It moves ICL away from being this purely emergent mystery towards being a mechanistically explainable phenomena rooted in core neural network computations, specifically involving these efficient, low-rank updates to the MLP layers.
But even with these massive steps forward, the authors themselves are careful to point out limitations, right? They still refer to it as a toy model in some respects. What are those main caveats and what technical challenges are still left on the table for future research?
Yes, and it's good scientific practice that they're transparent about this. Despite the breakthroughs, there are important limitations to keep in mind. First, their core derivation and analysis is primarily validated for a single transformer block. Real LLMs, as we know, stack dozens, sometimes hundreds of these blocks. How these implicit updates compose, interfere, or cascade across a deep stack of layers is a major open question. It's likely much more complex than just adding up single block effects. Second, their main theorem quantifies the effect of the context on the prediction for the very last input token only. It doesn't fully capture the mechanics of how the model generates subsequent tokens in a sequence, which is, of course, a primary use case for LLMs producing coherent extended text.
Okay. So understanding the multi-layer interactions and the full generation process are the next big hurdles.
Definitely. It raises really tough technical questions. How do these implicit dynamics interact across many stacked transformer blocks? Do the updates amplify, cancel out? Are there entirely new emergent phenomena that arise only in deep stacks? Does an update in block 5 affect the update process in block 10? And how can we extend this theory to explain the whole complex process of generating token after token, where the model's own previous outputs become part of the context for the next step? The technical challenges in modeling that multi-block, multi-token generation process, potentially involving sequences of compounding low-rank updates, are substantial. It likely requires new theoretical tools and insights.
So lots more work to be done. But looking ahead, even with these limitations, what does this deeper understanding of implicit learning mean for the future? How might it change how we design, train, or interact with LLMs? What are some speculative, purely technical applications this might unlock down the line?
Well, even with the open questions, this work provides really crucial insights into these emergent inference time capabilities. Understanding these implicit mechanisms is key, I think, to unlocking the next generation of LLMs. For instance, knowing that context drives these efficient low-rank updates to MLP weights could directly inspire new architectural designs. Maybe we could engineer ICL-optimized transformer blocks specifically structured to make this implicit weight modification process even more effective or precise.
Designing for learnability at inference time, essentially.
Exactly. We might also see new training paradigms. Perhaps models could be trained not just on downstream tasks, but also explicitly incentivized to develop stronger ICL capabilities, maybe by encouraging the attention layers to produce context vectors that lead to more beneficial implicit MLP reprogramming. And speculating purely on the technical side, this could be huge for highly adaptive, maybe even on-device AI. If an LLM can genuinely learn and specialize based on a user's unique context right there in the prompt, it can massively reduce the need for constant server-side fine-tuning and model redeployments.
Imagine a personal AI that just subtly adapts to your conversations over time.
Without needing huge data transfers or retraining runs, it could also lead to more precise ways to edit or steer LLMs. Maybe not just by fine-tuning, but by carefully crafting input prompts designed to induce specific desired implicit weight changes. That could offer incredibly granular control over model behavior, purely through prompt engineering, without ever directly touching the model's parameters.
That's a fascinating vision, models that are not just powerful, but truly fluid and adaptable in real time. We've definitely taken a deep dive today, haven't we? Moving from this mysterious in-context learning phenomenon to a concrete theoretical framework suggesting how LLMs might pull it off through these implicit weight updates. It's really a testament to the idea that even inside these incredibly complex AI systems, fundamental principles of neural network dynamics, like transforming inputs into weight changes, are still at play, just manifesting in new and sophisticated ways. We really hope this deep dive has given you, our listener, that shortcut to being well-informed, maybe sparked a few aha moments, and hopefully fueled even more curiosity about the technical frontiers of AI. And here's a final thought to chew on. If LLMs are genuinely learning, or something very much like it without explicit training, simply by implicitly reorganizing their internal weights based on the context you provide in a prompt, what does that really do to our traditional definition of learning in artificial intelligence? How might this continued blurring of the lines between static training and dynamic inference reshape the very architecture and capabilities of future intelligent systems? Could we see systems designed primarily around this real-time adaptation? For more deep dives into cutting-edge AI and ML research papers, and to stay updated on the latest technical developments in the field, be sure to visit our webpage. As always, you'll find the link right there in the bio. Until next time, keep exploring, keep questioning, and keep learning.